Next talk is by Amarda Shehu, and we're going to go from no data, some data, lots of data, to too much data. Okay.
Thank you. So Herbie said these are folks that are somewhat relevant or mildly relevant, and I love that characterization. So I feel like I need to justify a little bit why I'm here. Because I am in a computer science department, and I got my PhD in computer science mainly. I focused on AI at Rice. But I did have the opportunity to work for 3 years to be indoctrinated by a computational biophysicist. So I understand enough to be able to ask questions, but probably not enough to really challenge you on your answer or not to go very deeply. But when I started work, before the data revolution, my focus was a lot on three-dimensional structures, specifically protein structures, and I was really curious about bringing over some ideas from classic search or stochastic optimization and geometry and kinematics to sampling either alternative conformations of specific segments in proteins, such as loops, mobile segments, and then all the way to protein chains. So my focus was not really and never has been on structure prediction. Partly that was a survival mechanism because I realized early on as an assistant professor I could not compete with David Baker. But I could find my niche and focus more on sort of sampling ensembles and looking at dynamics. And that's what I did, but I mainly brought over these enhanced sampling ideas that were more ingrained in the AI than, let's say, what you would read by the amazing Sharaga and others. So I was a very late convert to deep learning. To this day, I don't like it very much. To be very honest with you, even though I characterize myself as an AI researcher, because we put a lot of creativity, even in our projects on machine learning, on how to represent and what information to encode and how to be smart about that. That's an aspect that I miss a lot. But in 2018, I had a student who beat my hard work of 2 years on a very classic recognition problem in antimicrobial peptides with a rather stupid deep neural network. He was happy, I was okay, we published a paper, but it was not a very pleasant experience. Since then, however, we could not ignore what's happening in deep learning, and so nowadays you don't find me so much at the Gordon folding conferences. So this is, in a way, I was telling Slava, because I served for a few years at NSF as an IPA, this is sucking back. It feels like I'm being sort of attracted back to this community, but mainly you'll find me in AI and machine learning venues. As a part sort of novel research and part preacher. There's a lot that is happening in the AI and machine learning conferences that is ignoring decades of very deep insight, what we're trying to do is bring that back into the models or into the way we evaluate these models to really understand what's happening. So some of the work we're doing now, for instance, is trying to bring some clarity. Can deep generative models really sample the structure space of a protein molecule, right? There's a lot of euphoria out there, so we're kind of cleaning up / advancing what's happening, but we're nowhere near. So we are able to generate credible looking tertiary structures just learning directly from, let's say, the protein data bank, but we're not able to condition them specifically on a protein amino acid sequence, and definitely we're not sampling the energy landscape of a particular sequence with these models. Though there's some interesting work by Frank, but in a little bit of a narrow context. Did some work on small molecules. I hinted at that when I asked the question. It's a somewhat simpler setting because you don't focus so much on tertiary structure. It's a graph, it's a discrete structure, but even there's a lot of work happening on how do you generate what we call with property control. So there's a lot of work we're doing on latent variable models where you try to learn underlying low-dimensional representation, right, the latent factors, and you try to connect these factors with properties that you want to control so that you can sample in a very specific space of your, in a very specific region of your molecular space that has the properties you care about, whether that's MIC, activity, low toxicity, ability to synthesize, lipophilicity, and so on. And very recently, we've started work on transformers. We've done a lot of work on transformers in the NLP domain, where we basically take pre-trained models, we fine-tune them, let's say, of psychology journals, and then we show that they're able to peak sort of mental health states over social media text. So basically, we're playing there. But very recently, we've become interested in how you can bring these ideas over to learn joint representations of protein molecules. So when I say join, in sequence, structure, and interaction space. And to me, that's very interesting because it's very hard for us sort of to rely on our creativity, and we try to do it for a long time, on how to bring these sort of multimodal data together so we could say something interesting about whether it's proteins or other biological molecules. But with transformers, you can, really leveraging the attention mechanism, you can try to build these joint representations, these joint embeddings, and then maybe you can support different prediction tasks or look more deeply and think about what that embedding is really able to do. Does it preserve, function colocalization, and so on. That's it.
Thank you. Anybody have a quick question? Or whoever, where's Neil? Where you get to set up while we're, okay. Yes, Jose.
I just.
Oh, thank you.
For the conformational space, do you think the problem is that we don't have good data, or there is sort of models? Is the models that cannot do it, and there is good data to sample conformational space for proteins?
I don't want to say we don't have good data, but I guess that depends how you go about it. What we wanted to do is this hypothesis that all the information you need is in the structure space, that you already have a good representation in, let's say, the protein data bank. To me, it's more of a creativity. How do you put together an interesting model that can then condition on a specific amino acid sequence? There are ways you can do it with reinforcement learning, but they're still they feel a little bit like you're putting components together, and we kind of want something a little bit cleaner. There are ideas, for instance, like Mulgan, right, where you have a reward network. You could do something like that to score the structures. It's not super interesting, but it could be, like, you could do that. You could play that game. Yeah.
Very quick.
A very, very quick question. I can understand that when you come to the problems you're interested in and you do some machine learning, you can speed up your structure prediction part of it. But not necessarily you're going to speed up your functional understanding. So what do you gain and what do you lose by going to your new approach compared to your old approach?
Yeah, I actually don't care about structure prediction. I have been very explicit about staying away from just structure prediction because you get only one structure. I've always wanted to see more complex molecules, right? So you can get different answers to that question. The one challenge for me is where is the important information? Let's say you want to go after a specific problem. Part of it is representation, and then what do I need to answer that problem? Can I answer that at the sequence level? Do I need the tertiary structure? Do I need to have information about, let's say, coming from protein-protein interaction networks? And then if I end up saying, well, I can sort of treat it as a hypothesis generation, but how do I integrate that information? How do I put that in a model? There are now it's a little bit easier to test this hypothesis.
But can you extract that information from your machine learning situation? That's what I'm trying to say. You can get a result in the end, but how do you extract which of these effects is important?
Yes, you can. You can do what we call an ablation study, which before we used to basically call turn on A and turn off B and turn off C. So you can say, okay, if I use sequence only, that's how far I can get. If I use both sequence and structure, that's how far. So you can get a sense of what is important. However, to look deeply, it goes back to interpretability, and I don't want to open that can of worms.
All right.